All right. Good afternoon, everyone. Thank you all for coming. So my name is Joseph, and I'm presenting work done in collaboration with Shija Hyo-Guan and Toby Gerstenberg. I'm a postbac researcher with Toby and Hyo at Stanford. So for today's talk, we shall ask the question, how do children use visual and auditory evidence to figure out what happened? So geologists combine information from fossils and sediments to reconstruct the distant past. So this is certainly impressive, but lay people like you and me make inferences about the past in our daily lives. So consider this meme I just pulled off of Twitter. You might find this funny in part because you can imagine some silly events that happened in the past to cause this apparent outcome. Or you can also consider this other example. So you're driving on the road, and suddenly you hear this loud siren sound coming from outside. Cars around you begin to slow down and peel off to the side of the road. So given all this visual and this auditory evidence, you might correctly infer that there's an emergency vehicle somewhere around you. So how do we make these inferences? Prior work has argued that our physical reasoning is driven by an approximate internal mental simulation model of the physical world. So this work has focused mostly on the visual domain, but causal inference is interesting because it relies on information from multiple sensory modalities. So for example, Smith and colleagues here argue that when a person watches a ball as it approaches and hits a tower, the scene is perceived through multiple sensory modalities, which are then combined to form an internal representation that contains probabilistic information about object properties in this scene, which are used to simulate various ways that the world might unfold using approximately accurate dynamics. So they call this the intuitive physics engine and posit that we could use it to predict future states of the world, infer unobserved states, make causal judgments, plan action sequences, and so on. So consider this Plinko box, which is a simple and intuitive way to assess people's physical reasoning based on multimodal evidence. It consists of a box into which a ball is dropped. So I'm just going to play a short animation of a drop just to calibrate your intuitions about how it works. So the sound, it was a bit low. Maybe we can play this one more time. Okay, perfect. So here's another drop from a different hole. Okay, good. So Gerstenberg and colleagues presented these very boxes to adults in two conditions. In the vision-only condition, they saw a still image just like this, containing the final location of the ball, and then they were asked to select in which hole the ball was dropped from. So why don't we all pretend that we were participants in this study. Given that the ball landed as shown, you can take a moment to just look at it. I'm going to use a virtual hand to point at one of the holes, and I would like it if you all responded by clapping if you think that's the correct hole that the ball was dropped from. Okay, so clap if you think the ball was dropped from hole 1. Clap if you think it's hole 2. Clap if you think it's hole 3. Okay, thank you. So Gerstenberg and colleagues developed a computational model to account for adult responses in this vision-only condition. Given the final location we just saw, this model runs noisy physical simulations of what would happen if the ball was dropped into the holes. So for hole 1, for example, this ball may have ended up between the pentagon and the triangle or beyond the triangle. The same is done for hole 2 and hole 3. It then computes the likelihood of the observed data conditioned on each hole by considering how close the ball ended up in each simulated run to where it actually landed. It combines this with the uniform prior over the holes to compute a posterior belief about where the ball was dropped. In this case, the model thinks the ball was dropped through hole 3, and so do adults, and so do many of you here. In the vision and sound condition, this box was first covered up, and participants heard the sounds as the ball was dropped. So once again, we're going to pretend we were in the study. Let's listen carefully for the sounds. Hopefully it's going to be loud enough. Okay, good. And then the box was uncovered, and the question was asked again. In which hole was the ball dropped? So here's my virtual hand again, if you heard those sounds. Given those sounds, can you please clap if you think the ball was dropped from hole 1, hole 2, and hole 3? Okay, good. The vision and sound simulation model encodes sounds as a vector that contains the time points at which the collisions happened. So for example, the ball collided with an obstacle here at t equals 37 milliseconds and then lands in the sand at t equals 77. To compute the likelihood, the model then compares what this vector looks like in the actual situation to what it looks like in each simulated run, as it did in the vision, for example. To compute the likelihood of this auditory data, it considers how close the sounds of a simulated run match the sounds that were actually heard, and combines it with the likelihood from the visual data, and based on a uniform prior over the holes, again, this information is used to compute a posterior belief about where the ball was dropped. In this case, the model thinks the hole is dropped in hole 2, so do many adults, and so do most of you here. So beyond prior work that focuses on vision-based inferences, this Plinko task shows how computational modeling can help us understand how people integrate information from vision and sound to figure out what happened. But how does this ability develop in early childhood? So prior work has found that children, like adults, also possess an intuitive and theory-like understanding of the world that may provide the foundation for such multimodal inferences. Hood and colleagues, for example, presented children an apparatus with curved tubes and asked them to locate the ball after it was dropped. They found that younger children tended to search in the bucket directly underneath, irrespective of how the tubes were set up. So based on this, you might expect that young children, when presented with this Plinko task, might simply choose the hole that is closest to the final location of the ball, and they may show better performance as they get older. In another study by Siegel and colleagues, children heard the sounds as two boxes were shaken, each of which contained the same target object from a corresponding pair. When asked to select which box they would open to find the target, they used the auditory information to successfully choose the box for which it would be easiest to discriminate the sounds. So based on this, we might expect that children above 5 or 6 years of age, presented with this Plinko task, may also be able to consider the auditory information. However, we do not know whether children are actually able to integrate the two. Yes. So this Plinko task offers a way to ask not just whether children succeed at multimodal integration, and at what age, but it also helps us understand what strategies they use and how these might change in development. So we ran a pre-registered study via Zoom to 64 participants aging 3 to 8, whose racial and ethnic demographics were more diverse than the US national average, but were generally of higher SES. We recruited the mascot Elmo to help present the stimuli. So for the procedure, we first went through a familiarization phase to ensure the children understood how the box worked. This consisted of watching Elmo freely play with the boxes as such. Next, they learned about the holes and the obstacles in the box, which were highlighted as such. So now we're highlighting the obstacles. And then next up, they learned about the sounds made by the ball, so namely the beep, the chick sound, and the boom sound. Then they played one practice round with Elmo, in which they saw a drop, and they were asked the test question, in which hole did Elmo drop the ball? In the pretrial phase, they played 2 more practice rounds, but similarly, they could still see which hole Elmo had dropped the ball from. And finally, in the actual trials, everything was occluded, and then the test question was asked after the ball was dropped, and everything uncovered again. Each child was presented with 9 trials in a within-subjects design, and we selected these trials to generate maximally different predictions across the 4 models that I'm going to talk about. So here's an example of a participant that we ran. So here we are in Elmo's pink room. Are you ready to play? Let's go.
Yes.
And here's the ball. In which hole did Elmo drop the ball?
If you saw my finger, I think it's the green one, and it slid onto the shape under the green one, and then it slid off of that shape and landed right where it is.
Good. So you may have actually noticed that he chose the incorrect hole. It was the yellow hole. But what I'd like you to ask yourself is, what strategy did he use to arrive at his answer? And that's exactly what we did in the study. So here's a quick preview of the raw data. In each of these bar charts, one of the bars is highlighted to indicate the correct response. So for example, here, most children selected hole 2, whereas the correct answer is actually hole 1. We analyzed our data set by looking at children's accuracy with respect to ground truth, and then we did a model comparison based on their choice of holes. So we plotted accuracy as a function of age, which we treated as a continuous variable. Here's the adult data first. So unsurprisingly, they're more accurate with both sources of evidence than with just one. But how does this compare to children? Well, here are the children. Overall, we see an increase in accuracy with age. However, only 8-year-old children are actually reliably above chance. It's also worth noting that even adult performance was not at ceiling on this task. So based on this plot, you might think, okay, so 8-year-old children are doing sort of okay, clearly above chance. 7-year-olds are getting there, and the rest are pretty much performing at chance. So I think there's more to this story, because even though these responses show chance performance for most, theory-based modeling can help us reveal the different strategies these responses reflect. So we compared these responses to the predictions of 4 models that formalize different strategies that children might be using. The simplest possibility is that they just might randomly choose between the holes, and this is implemented in the guessing model by assigning an equal probability to all the holes. Another possibility is that they use a simple matching heuristic and choose the hole that's closest to where the ball landed, consistent with prior work on the gravity bias. The matching model implements this by assigning a probability to each hole based on the horizontal distance between the center of the hole and where the ball ended up. The closer the ball is to the center of a hole along the x-axis, the more probability is assigned to that hole. Another possibility is that children run mental simulations that take into account only the visual information. This is implemented by the vision-only model that we discussed earlier. And finally, another possibility is that they run mental simulations that integrate both the visual and the auditory information. This is implemented by the vision and sound model, also that we discussed earlier. So here are the model predictions for some of the trials. For example, the vision and sound model in this particular trial thinks that the ball was most likely dropped in hole 1. This is colored in purple, I believe. So how did we use this data to compare the different candidate models? Well, so if a hypothetical participant selected or responded with hole 1, let's say for each of these trials, this would correspond to hole 1 of the bar charts at the bottom. We would calculate the likelihood of that data for each of the models. And how did we do that? Well, the vision and sound model, for example, predicts the following values for hole 1. So these probabilities are then combined multiplicatively as such. We would do the same for the matching model predictions, and so on for the rest. We then use Bayesian inference to compute the probability of each model given the data, assuming a uniform prior over these models. In this case, the data is most likely under the vision and sound model. But this is just a hypothetical example, so let's see the actual model posteriors. So the figure here shows the posteriors over the models for each participant. When we highlight the children whose responses are consistent with both of our simulation models, we see an overall increase in children's tendency to engage in simulation. And by consistent with here, I just mean children for whom the sum of posterior probabilities is greater than 50%. So here we aggregated the posteriors across age groups and compared it with adults. So for adults, you can see that their responses are more consistent with the simulation models when they have both sources of evidence than when they have just one. For the children, they appear to be transitioning gradually from mostly relying on a simple matching heuristic to relying more on physical simulation, first by only considering the visual evidence, and then eventually by considering both the visual and the auditory evidence. Okay, so in conclusion, we asked 3 to 8-year-old children to infer in which hole a ball was dropped in the blink of a task. What did we find? Well, 3 to 3-year-old children, even though performing at chance, they're not randomly guessing, but are systematically selecting the hole that's closest to where the ball landed. We see clearer evidence for multimodal simulation in older children. By age 8, children utilize both sources of sensory evidence when inferring where the ball was dropped. Critically, we find that a model-based analysis helps us go beyond the whether and the when to understand what strategies children use and how these change with age. Now, some related work I'm excited about has explored mental simulation by collecting eye tracking data as adults solve these very Plinko boxes. So if you're interested in this kind of thing, please go to my colleague Ari's poster session at 3 p.m. today. Ari is a graduate student with Toby Gerstenberg. So that's all. Many thanks to my collaborators, our labs, Social Learning Lab, Causality and Cognition Lab. I'm happy to take any questions.
Really nice talk. Just about the timing information, well, the sound information, it occurs to me that there's potentially both qualitative information in terms of how many bumping sounds there are, but also like the precise delays between them. I'm wondering if you think you have any evidence that people are, kids or adults, are sensitive to the timing of the sounds as well as just how many of them there are.
Yeah, good question. So in the vision and sound simulation model that I just discussed earlier, I don't think I went into too much detail, but one of the ways that the model captures the sounds is it doesn't just capture the difference in time between the time points of the collisions in the actual situation and in the simulations, but it also captures the number of vectors. The number of collisions within the vector. And it basically incurs a penalty when the number of collisions in a vector in a simulation does not match the number of collisions in the actual situation. And this is the model that we compared to the actual empirical data to find that many people's responses are matching that pattern. So I feel like we captured that in the model. And I do agree that possibly people were definitely considering not just the whether or not a collision happened, but how many collisions were happening. Yeah, does that answer your question?
Sort of, yeah. Well, I was wondering if you dropped out the timestamps but just kept the length of the vector, you might get almost as good a capturing of many of your participants. So it's sort of going the other direction. People might be more heuristic than the model suggests, maybe, for some of them.
Yeah, that's a good suggestion. I'll consider that. Thank you.
Thanks.
Hi, that's a great talk. I was interested just in general with all these multi-sensory tasks, like auditory information is transient, so the auditory evidence, they can't revisit it, whereas they're like constantly looking at the, picture of the Plinko box. So do you think that kind of thing, like the fact that, they really have to be paying attention to be able to like remember or have encoded the auditory sounds, like was that interact with any of your developmental effects, you think?
Yeah, that's certainly a good question and a very legitimate, I guess, explanation for why this task might be harder for younger children. So, as you all also observed, you're making a live observation of the scene, but the sound isn't there. The sound is really just like a memory trace. And so for younger children, they're not just using the visual information, they're having to remember how many sounds they heard, what types of sounds, because there were different sounds. There was a beep sound, there's a boom sound, there's a chick sound. So it's possible that this particular paradigm just has pretty demanding cognitive demands for younger children, and we could ideally get at mental simulation with younger children if we had like a much simpler paradigm that had maybe a smaller number of sounds, or maybe online integration rather than integration relying on information presented in the past. So I definitely agree with your concerns. Hope that answers your question.
Terrific talk, and I love this work. I have a minor and friendly suggestion, because I made the same error that I think maybe your children are making on the task, which is there's no sound for the final drop into the sand. Right, so you hear the sound for hitting the obstacles, you don't hear the sound for the sand. And realistically, you would, right? So if the ball plunks on the sand, you would hear it. So I would suggest, because I think this is totally gorgeous, but I also think children can do mental simulation of integrating vision and auditory stimuli pretty well before they're 3, because the box shaking tasks, right, they're quite quantitatively accurate from 4 to 8. So I wonder if you add a distinctive sound for the final drop, if you're going to improve your developmental data, you may still find, many things in the conflict with matching and the transience of the auditory stimuli could really be playing a role. But before we know all of that, I would suggest just making sure that the younger children, the older children are presumably learning from what you tried to show them, which is, oh no, it's only going to make a sound when it hits the obstacles. The younger children just might not be getting that task demand, and they may be assuming there's also a drop, because that child's explanation for the wrong answer was flawless, right? But he was counting, I think, something different, and actually made the same mistake that he did. So that's all. I think it's a gorgeous work.
Thank you, Laura, for that suggestion. So this actually wasn't made very clear, but there is a third sound, or there is a sound that the ball makes when it hits the bottom. The thing is, so when we designed this paradigm, what was put at the bottom is sand, so there's actually sand there. So when the ball lands, it makes this sort of muted sound. We're calling it a chick sound. But I think it is a very qualitatively different sound from the sound that the ball makes when it hits the obstacles, which was an intentional decision. But I think I've actually quite noticed this, yeah, for some people, it's like such a muted sound that maybe some people don't actually capture it. And because these studies were done over Zoom, you never know. Someone's computer sound may have been really low. They couldn't actually hear the last sound, but they would ideally still be, making the correct inference because they're counting the number of sounds and, considering that this is the sound that the ball made when it hit the bottom. So I agree with you that having it be very clear what sounds are being made at what collisions would give us much more clearer data for the children. But yeah, thank you for that suggestion.
Any further questions? Good.
These questions made me think about salience, because salience and attention might play a role here in terms of the ability to combine the 2 dimensions. And you didn't vary salience by varying, I don't know, the sounds, the auditory degree, and maybe the visual degree, and so on. But salience is surely playing a role in whether you do or don't combine these properly.
Yeah, thank you for that. Yeah, we certainly could perhaps run a study that just varies how strong the auditory evidence is, for example, by manipulating, like you say, the salience of different sounds. And maybe we can get at a sort of graded ability to not just get the correct response, but also the model's ability to sort of capture your strategy. So some people with very weakly salient auditory evidence, I suppose, would be not performing as well as people with strongly salient evidence. I think this is what you're suggesting, but yeah, I guess the idea is that you would get at a difference in degree of accuracy or of simulation, I guess, strategies, depending on how strong your evidence is, which I think is also a fantastic idea for a future study. I hope that answers your question.
So that's the end of the session, if I'm not mistaken. Let's applaud Joseph again. Thanks for coming.